All right, let's talk about Newton's laws of motion. And I want you to just forget for a minute that these are some dusty old rules from a textbook. Think of them more like a toolkit, you know? A set of keys that lets you decode and even predict how pretty much everything in the world around us moves.
I mean, it seems a little crazy, right? How can the exact same principles explain the explosive jump of a tiny little grasshopper and the slow, controlled landing of a giant jetliner? So how is that even possible? Well, the answer starts with a really crucial first step that physicists use to make any problem way clearer. Before you can even think about plugging numbers into an equation, you have to actually see what you're dealing with. And that means we have to visualize all those invisible pushes and pulls that are acting on an object. This is where we bring in what is, honestly, the single most important tool for this kind of problem. It's called a free body diagram, and the genius of it is just how simple it is. You take a really complex situation, a car driving, a book on a table, and you boil it down to just a single dot. Then you draw arrows coming out of that dot for every single force acting on it. It's all about making sense of the chaos. The best part is how this turns a messy situation into a neat little puzzle. You just go down the list. Is gravity pulling on it? Yep. So you draw a downward arrow. Is it sitting on something? Well, that surface is pushing back. We call that the normal force. So you draw an upward arrow. Is a rope pulling it? That's tension. And the size of the arrow matters too. A bigger force gets a bigger arrow. It's a full visual inventory before you do any math at all. So here's a perfect example. A person just standing still. You've got gravity, which is labeled W here, pulling them straight down. But they're not falling through the floor, are they? That's because the floor is pushing back up with a force that's perfectly equal and opposite, which you see as WA. The forces are balanced, the arrows are the same length, and so nothing moves. Okay, so once we've got our diagram and we've identified all the forces, we can take that visual map and plug it into what is maybe the most powerful equation in all of classical physics. This is where it all comes together. All those arrows, all those different pushes and pulls that we drew out so carefully, they all feed into one single beautiful formula that tells us exactly what that object is going to do next. And here it is. You've probably seen it. Newton's second law. The F here stands for net force. That's what you get when you add up all those arrows from your diagram. If all the forces cancel each other out, the net force is zero, and the object doesn't accelerate. But if there is any imbalance at all, even a tiny one, the object has to accelerate. This little equation is the bridge from our drawing to a real prediction. So let's put a number on it. This, 1,600 newtons, is about the average force it takes to get a billiard ball moving, but in just 4/1000ths of a second. Now, a newton is just our unit for force, and 1,600 of them is a lot. We're talking about a force that's like lifting 360 pounds. But here's the kicker, and why context is everything. That huge force is acting for such an incredibly short amount of time that the final speed of the ball is, well, it's not that spectacular. It's just a normal speed for a billiard ball. It really shows you how force, mass, and time all have to work together. All right, now for the big one, Newton's third law. This is the one everybody quotes, but it's also probably the most misunderstood of all of them. And we're going to use a classic example to show how our gut feelings can sometimes get it totally wrong. So just think about it for a second. We've all seen this kind of thing, unfortunately. A small car hits a big truck. Which one do you think gets hit with more force? What's your gut reaction? Most of us go one of two ways. Either we think, well, the car gets way more damaged, so the force on it must be bigger, or we think the truck is so much bigger and heavier, it must be delivering a bigger force. Both sound pretty reasonable, right? But they're both wrong. And this is the completely counterintuitive truth of Newton's third law. In any interaction, any collision, any push, any pull, the forces are always equal and opposite. The force that the truck puts on the car is the exact same size as the force the car puts on the truck. Period. So if the forces are equal, why does the car get absolutely mangled? Well, it all goes back to our master key, F equals m times a. Since they both feel the same F, the object with the smaller m, the car, has to experience a much bigger a huge acceleration. And that massive, violent change in motion is what does all the damage. Okay, so these laws aren't just for car crashes. They actually explain things we feel every single day, often without us even realizing what's going on.
So imagine someone weighs about 610 newtons. That's roughly 137 pounds. They're standing on a bathroom scale in an elevator that's not moving. That number, 610, is their baseline. It's just the pull of gravity on them.
But now, the elevator starts accelerating upward, and for a second, the scale flashes 730 newtons. Why? Well, here's the secret. A scale doesn't actually measure gravity. It measures how hard the floor is pushing up on you. That's the normal force. And to make you accelerate upwards, the floor has to push on you harder than gravity is pulling you down. That extra push is what you feel as being heavier.
And the exact opposite happens when you drive over a hill. You know that little whoop feeling you get in your stomach? At the very top of that hill, your body is changing direction. It's accelerating downward to follow the curve. Because of that, the car seat doesn't have to push up on you as hard. That normal force goes down. And for just a split second, you feel lighter.
Okay, so we've got our free body diagrams, we've got F equals ma, and we've got action-reaction. Let's put all the pieces together and use them to solve a classic physics puzzle that really ties it all up.
This little contraption is called an Atwood's machine. It looks really simple, right? It's just two weights connected by a string that goes over a pulley. But it's the perfect little system for seeing how forces can compete with each other to create motion.
When you first look at it, trying to figure out the motion is, well, it's awkward. The forces are all over the place. One mass is being pulled down on the left, the other is being pulled down on the right. The original source I looked at called it an uncomfortable shape for analysis. And I think that's the perfect description.
And this is where the physicist's mindset comes in. If the problem's weird, just change the way you look at it. We can mentally unfold the whole thing and imagine it as a straight horizontal tug-of-war. On one side, you have gravity pulling on the first mass. On the other side, you have gravity pulling on the second. All of a sudden, figuring out the net force and the acceleration is so much easier to see.
And really, that's the whole point. This isn't just about solving problems in a textbook. It's about a new way of seeing the world. Right now, as you're sitting there, gravity is pulling you down, your chair is pushing up, Newton's laws are happening all around you all the time. The real fun is learning to spot them. So, what forces are acting on you right now?